Okay, for Chapter 2, Section 1, we're going to be looking at limits and secant lines and tangent lines and different things. So most of these are going to be tables we fill in, so hopefully nothing too challenging. So if we look at this, it says, the flash unit on a camera operates by storing charge in a capacitor and releasing it suddenly when the flash is set off. The data in the table describe the charge Q remaining on the capacitor measured in microcoulombs at time t, measured in seconds after the flash goes off. Use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t equals 0.04 seconds. Note the slope of the tangent line represents the electric current flowing from the capacitor to the flash bulb measured in microamperes. In the figure we plot the data and use to sketch a curve that approximates the graph of the function. Given the points P, 0.04 and 67.01 and R, 0.00, 100 on the graph, we find that the slope of the secant line PR is what? Okay, so what they want us to do here is they want us to put in the this is slope formula. So it's the change in Y values divided by the change in X values. So this is really X1, Y1, and this is X2, Y2. And slope formula says, take y2 minus y1 divided by x2 minus x1. Now they've already plugged in y2, and we had to plug in y1, which would be 67.01. And they've plugged in x2 and x1. So we just have to subtract 100 and 67.01. Okay, and if you plug in 67.01 and subtract it from 100, you get 32.99. Divide that by the denominator, which is just 0.04, and you should get, and actually this should be a negative 824.75. Okay, then it says the table at the left shows the results of similar calculations for the slopes of secant lines. From this table, we would expect the slope of the tangent line at t to lie somewhere between negative 743 and negative 606.150. In fact, the average of the slopes of the two closest secant lines is, so what they're doing is they're saying if you add two of these slopes and divide by 2, or multiply by 1/2 is what they did, you will get the average of these secant lines, and that happens to be, you should get negative 674.75. So we're going to estimate the slope of the tangent line to be exactly that, negative 674.75. Oh, to the nearest integer, we're going to call this negative 675. And if we check those, we should have all those correct. So they just want us to go in here and kind of follow along, plug in these numbers and do a few arithmetics, subtraction, division, not too bad, and we'll get that. Okay, then they say another method to do this is to form a triangle here. So this is really no difference. So this triangle, the sides would be the change in the Y value, the change in the X value, which is slope formula. So you get approximately the same kind of answer. Okay, let's look at problem 2. We're going to have a similar kind of problem. It says, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 7 seconds. So it says, through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any free-falling object is proportional to the square of the time it has been falling. This model for free fall neglects air resistance. If the distance fallen after t seconds is denoted by s of t, and measured in meters, and Galileo's law is expressed by the equation, distance as a function of time is 4.9 times the time squared. Okay, it says the difficulty in finding the velocity after 7 seconds is that we are dealing with a single instant of time. Time is 7, so no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second from 7 to 7.1. So they take the position at 7.1, and so that's just going to be 7.1 squared minus the position at 7, so it's just 7 squared, and then you're dividing by that change in time, which is 1/10 of a second. So if you square 7.1 and square 7 and then multiply each by 4.9 and subtract, you will get about 6.909 on top, and when you divide by 1/10, it just in essence multiplies by 10. Move the decimal place 1 to the right, you'll get 69.09. Okay, so in fact that's right here in the table. So we just calculated that value. And then what they do is they shrink this time. So the first time was 1 second and the average velocity was 73. Then they shrink that time interval down to 1/10 of a second and it's 69. Then they shrink it down to 5/100ths of a second and you get 68. And then 1/100ths of a second and you get 68 again. And then 1,000ths of a second you get 68 again. So these are all getting closer and closer to 68. So there's kind of it's kind of converging on a value there. Okay, so it says, it appears that as we shorten the time period, the average velocity is becoming closer to, rounded to 1 decimal place, we would call it 68.6. 68.6 meters per second. The instantaneous velocity when t equals 7 is defined to be the limiting value of these average velocities over shorter and shorter time periods that start at time equals 7. Thus, the instantaneous velocity after 7 seconds is the following. Round your answer to 1 decimal place. It's the exact same thing. So it should be 68.6. So basically, as we shrink that more and more, it's getting closer and closer to 68.6. And these are called limits and instantaneous velocities versus average velocities. And we're eventually going to expand on that even more with derivatives. So very useful opening topic for this idea that we're going to study quite a bit later. Okay, so for number 3, we're going to have to do a little more work. We don't have these nice tables where we just have to fill in the values. It says a cardiac monitor is used to measure the heart rate of a patient after surgery. Compiles the number of heartbeats after t minutes. When the data in the table are graphed, the slope of the tangent line represents the heart rate in beats per minute. So we have the monitor estimates this value by calculating the slope of a secant line. Use the data to estimate the patient's heart rate after 42 minutes using the secant line between the points given with the given value of t. So the slope of the secant line it's just another slope formula, so it's going to be y at value t2, if we're doing time, minus y of value time 1, divided by time 2, minus time 1. So in the first problem, they tell us the two times are 42 and 36. So it's 42 minutes minus 36 minutes. Now these y values are just these heartbeats. So this heartbeat row is y at different times. So for 36 and 42, we need this number and this number. Just these actually, the red ones. So at 42 minutes, the patient's heartbeat is 29. I kind of overwrote it there. Overwrote it. 29:59 minus. Let me make sure I read that. Okay, 29:59. Yep. Minus at 36 is 25:47. And we're going to get. Okay, so we're going to get 412 heartbeats on top, divided by 6 minutes on the bottom. So we're going to have an average heart rate in between those two time frames of about 68 beats per minute. Okay, and let's see, they want us to round to 1 decimal place, so we will call this 68.7. And then you're just going to repeat this process. The only thing you're going to change is so 42 until the last one. I don't know why they changed it. So the bottom number, the first number is always going to be 42, and then you're going to change it to 38, and then 40, and then you just have to pull the right numbers from the table. So you repeat this process, and I'm just going to show us the answers here. And if you continue in this fashion, so you're just changing the top two numbers to these red values depending on which time frame you're looking at, and then the bottom numbers just change according to time. You should get these values, or whatever your table shows. So notice it's going from 68.7 to 67.8 to 66.5 to 66. So you can kind of see how it's converging onto this 66 value. Okay, and that'd be problem 3. Okay, problem 4 is going to be very similar. We're going to calculate the slope of a secant line. So we have the point P, 7 minus 2 lies on the curve, y equals 2 divided by 6 minus x. If Q is the point, x, 2 over 6 minus x, use your calculator to find the slope MPQ of the secant line. So MPQ is going to equal, your y value is going to be 2 over 6 minus x, minus, so that's for point Q, but for point P, your y value is always negative 2. Then we're dividing by the x value that we're going to pick for this point Q minus the x value for point P, which is always 7. So this is going to be 2 over 6 minus x plus 2 all over x minus 7. And you're going to notice that x cannot be 7 here. So if you pick 7, you get divided by 0. So what we do is we pick numbers close to 7 but not equal to 7. So we pick numbers smaller than 7 like 6, 6.9, 6.99, getting closer to 7. Then we pick numbers bigger than 7, 7.1, 7.01, 7.001. Both are getting closer to 7 but not ever letting it equal 7. So let me just do 1 and then I'll kind of put in the answers for the others and we can talk about it. So let's say we put in 6.9. This would be 2 divided by 6 minus 6.9 plus 2 all over 6.9 minus 7. And that is going to equal, okay, so if you reconcile the top, you'll get this fraction turns out to be negative 2.222. Plus the 2 would make that this leading 2 and this leading 2 will cancel, so you just get negative 0.222. And then 6.9 take away 7 is negative 0.1. If you divide those two, the negatives cancel. And this is basically whenever you divide by a tenth, you just shift the decimal 1 to the right. So it becomes positive 2.22. Okay, and then let me put in the rest of the answers. Okay, so if you plug in these other numbers into the same formula, you're going to get bunch of 2's. They want 6 decimal places, so be careful here. Then when you make 6.99 for x, your slope is 2.0202. At an x value of 6.999, your slope is 2.002. Then 2.0002. If you notice, these numbers are getting closer and closer to 2. Now what's interesting is when you make the numbers bigger than 7, you get smaller values. So you get 1.18, then 1.98, and actually I think I just discovered a typo here. This should be 818181. Okay, then 1.98, and then 1.99, and 1.999. So from numbers bigger than 7, they're getting closer and closer to 2. And from numbers smaller than 7, they're getting closer and closer to 2. So we're going to say that the actual slope of the secant line is 2 on the dot. Okay, then they want us to calculate the actual equation for the secant line. So the equation for the secant line is equal to the slope of the secant line times x plus some b. And they give us the point 7.2. So that's x and that's y of the secant line. So we plug in minus 2. We plug in the slope of 2, and the x value is 7, and we can solve for b. So we'd get minus 2 equals 14 plus b. Subtract 14 from both sides. B is equal to negative 16. So we can type in here, I think they're going to want us to type it as y equals 2x minus 16. Okay, and we have all those correct. So it's not meant to be difficult math, it's just repetitive. So you're going to do this slope formula 1, 2, 3, 4, 5, 6, 8 times. So you are going to do this 8 times. It is helpful if you have a graphing calculator, you can program functions in. That's how I did it. And so all you have to do is change the x value and just spit out the proper number. And then you have to just do this slope intercept form of a line. You know the slope is 2, and they give you 1 point, an x and a y. Replace those, you can solve for b. Okay, so that would be problem 4. Okay, 5 is really no different. We're shooting an arrow upwards on Mars, the Martian surface. So it has a speed of 58 meters per second. Its height is in meters, t seconds later, given by this equation. And it wants to find the average speed over the given time intervals. So the average speed, which we can call v average, is just, again, it's just slope formula, no different. It's the y value at time 2 minus the y value at time 1 divided by the difference in times. Okay, so in this problem they give us 2 times 1 and 2. So the first number is t1 and the second number is t2. And they are 1 and 2. So here's how you do this. You plug in 2 into this y equation here. So it's going to be 58 times 2 minus 1.86 times 2 squared. Now, I would probably use brackets for this because I'm subtracting then, plug in times 1. So it's going to be 58 times 1 minus 1.86 times 1 squared. And then the bottom is very simple. It's just 2 minus 1. Okay, so let me get the numbers for that. Okay, so if you plug in these numbers, the first one, when time is 2, you get 108.56. When time is 1, you get 56.14. The difference in 2 and 1 is easy. It's just 1. So subtract those two numbers, you get 52.42. So that's the average speed of this arrow from second 1 to second 2 on this Martian surface. Now, what they're going to do is they're going to shrink this number, the second number, down. So they're going to make it closer and closer to 1. So they go to 1.5 and you get 53 meters per second. You go to 1.1, you get 54 meters per second. 1.01, very close to 1, you get 54.26. 1.001, even closer to 1, you get 54.28. So what you're getting is these numbers are converging on a value. And you can see that they're getting closer and closer to the same number, 54, and a little bit of change there, 0.28, 0.3, something like that. So that's what we call the instantaneous velocity when time is 1. So it's like, okay, I've averaged my arrow over this time interval, but what's the instantaneous speed of that arrow at this given time? 1 second, and that's just what these numbers are converging to as you shrink your time interval closer and closer to just 1 second. Okay, that's problem 5. 6 is going to be exactly the same way. We just have a different equation, but even our time intervals are the same. So let's give this one a look. It says the displacement in centimeters of a particle moving back and forth along a straight line is given by the equation of motion. S equals 5 times the sine of pi t plus 5 cosine pi t, where t is measured in seconds, round your answer to 2 decimal places. Find the average velocity during each time period. So v average, it's going to be s, the displacement at time 2, minus the displacement when you plug in time 1 over time 2 minus time 1. Now let's look at this one, because we have a trig function, so it's a little more complex. Time 2 is again 2 seconds in this one, and time 1 is 1 second. So everywhere I see a t in this s equation, I'm going to change it to a 2. So we get 5 times the sine of pi times 2, which is the same as 2 pi, plus 5, parentheses, plus 5 cosine of pi times 2, which is 2 pi. That's all for time equal to 2. Then we're going to plug in time equal to 1. So you get 5 sine of 1 pi plus 5 cosine of 1 pi. And we're dividing again by 2 minus 1. Okay, so let me get those numbers. Okay, so make sure you're in radian mode when you do this. If you do sine of 2 pi times 5 plus 5 cosine of 2 pi, you'll get 5. When you do 5 sine of 1 pi plus 5 cosine of 1 pi, you'll get negative 5. But double negative will make this positive 10, and then the denominator is 2 minus 1, which is 1, so it's just 10 over 1. Now what's interesting about this is when you shrink this down closer to 1, it actually goes from a positive number to a negative number. So this one changes quite a bit. But you will see convergence. So you'll get negative 13, then negative 15.46, then negative 15.68, which means it is becoming the instantaneous velocity of minus 15.68. Problem 6. Okay, so the last problem in this set is very similar to one we did up above, and they're going to give us a line, y equals x minus 2, the square root of that, and it says the point 3, 1 lies on this curve. If q is a point, x minus 2 square rooted, use your calculator to find the slope of the secant line. So the slope of the secant line is going to equal y2, which is going to be the square root of x minus 2, minus y1, but y1 is always going to be 1 from this point, divided by x, which we can pick to be anything, and then minus x from the point is 3. So in this first one, the x value is 2.5. So we just have to replace this with the square root of 2.5 minus 2 minus 1 over 2.5 minus 3. And we'll get on top. Okay, so if you plug in these values, you'll get 0.58. And yeah, again, you have to go to 6 decimal places, so be careful here. I wrote down 7 decimal places so I knew how to round. And you should get these numbers, so 0.58, 51, 50, 50, 0. So when x is close to 3 but not quite 3, we get 0.50. Then we go numbers bigger than 3, so 3.5, 3.1, 3.01, but they're getting closer to 3, and you get, again, 0.44, 48, 49, 49.9. So they're getting instantaneously closer to 0.50 on the dot. Okay, then they want us to find the slope of the secant line at that point. So y secant equals m secant times x plus b. This is going to be x, this is going to be y secant. So we'll replace y secant with 1. M secant we calculated to be 1/2. X in this problem is 3 plus b. We'll get 1 equals 1.5 plus b, subtract 1.5 from both sides, we'll get negative 0.5 equals b. So when we put that all together, we should get y is equal to 0.5x minus 0.5. Now they might actually want fractions here instead of in fact I think they do. I think they want you to type this as 1/2, and this would be x over 2 minus 1/2. Be very careful how you type this. It will be a little picky there. Okay, so that is the proper values there. Now we want to sketch this. So the sketch of this, and they've zoomed in, would be the slope is positive 1/2 minus 1/2. So it has to go up and to the right. And this curve, the square root of x minus 2, maybe I can just do a better job of sketching this myself. So let's try this. actually, better yet, okay, let's graph this. So it's the square root of x minus 2, and we're looking at the point x equals 3, so right here, 1. So that's the point we want. Let's see if I can show this in one screen. Okay, so the slope of the tangent line at that point let me do it in blue, right at 3, that's 3, here's 3, 1, right there. This is that's the tangent line. So this line has a slope, a rise over run of 1/2. And if we were to extend it, it would cross at negative 1/2. So this, I'm going to use color. This point would be minus 1/2. That's the y-intercept. And then this slope is positive 1/2. So for pictures go, the only one that really makes sense, that looks right, is this bottom left one. So let's go select that one, and let's try it. And it liked my rounding for all those, and it liked this in exact form, 1/2, x over 2 minus 1/2, and then the only picture that matched what we saw in Desmos and what I drew was this bottom left one. Okay, so that will be section 2.1.